Hi everyone, welcome back to DataToCrunch. My name is Rutuja, and today we will try to continue with our next part of Spark and Databricks. So today we will try to cover mainly Spark architecture, then the driver node architecture, worker node architecture, then the memory management concepts which are on-heap and off-heap, then garbage collection, and lastly we will try to look at Spark application workflow. So now let's have an in-depth overview about Apache Spark architecture. So Apache Spark's architecture is mainly designed to optimize distributed data processing by leveraging in-memory computation, then the parallelism, and then scalability. So it consists of various components that work in harmony to execute the Spark application very efficiently. So we will try to have a look on this structured Spark architecture. So the main key components of Spark architecture are driver program, executor, and then the cluster manager. So we will firstly look at driver program. So the driver is a central component which is mainly responsible for controlling the execution of Spark architecture. So if we talk about the responsibilities of this driver program, then we can say that it is responsible for submitting the application by creating the Spark contest, then splitting jobs into smaller tasks and distributing them into executors, and then maintaining the metadata about the application. That is nothing but, for example, maybe job progress or the task completion task or status, such kind of things. And then lastly, we can say that it is also responsible for communicating with the cluster manager to request the resources and with the executor to manage the tasks. So the next component is executor. So executors, we can say, are distributed processes that are running on the worker nodes of the clusters. So if we talk about the responsibilities of the executors, we can say that it executes the tasks which are assigned by the driver. Also, it stores the intermediate data or cached RDDs for the reuse, and it also sends the computation results back to the driver. So each executor has two key areas of memory. So the first is execution memory, which is responsible for performing the computations, and then the storage memory, which is responsible for caching the data. Then the next component of architecture is the cluster manager. So the cluster manager oversees the resource allocation for the Spark application, and it also ensures that executors receive the necessary CPU cores and the memory. So this cluster manager is supported by some of the components which are like standalone mode, which is Spark's native cluster manager, then the Yarn, which is common in Hadoop ecosystem, then Apache Mesos, which is a general purpose cluster manager, and then the Kubernetes, which is ideal for containerized deployments. Now let's see this driver node architecture in detail. So the driver node is a central component of Spark application which is responsible for managing and maintaining all the critical information throughout the application's lifecycle. So especially it is a process which is running on a physical machine that oversees the application state while interacting with the cluster. Okay, so now we will break down its functionality and we'll look at it. So the first one is this driver mainly runs as a JVM process. JVM is nothing but Java Virtual Machine. So let's see now, when this user submits the code to the driver, it initializes its Spark session. So the driver converts this user code, which is containing any kind of transformation and actions like filter or map, such kind of things, into logical execution plan, which is known as DAG, that is directed acyclic graph. So this DAG scheduler, it generates the logical execution plan, and it begins the building of lineage graph. So when an action is invoked in the code, the processing of actual data begins. So this DAG is divided into smaller execution units called these stages, which represents a set of interdependent tasks. So the logical execution plan is further transformed into a physical execution plan, which comprises these tasks grouped under each stage. So this DAG scheduler hands over these tasks to the task scheduler, which negotiates resources with the cluster manager. So the cluster manager launches these executors on the worker node on behalf of this driver. And at each point, the driver assigns this task to the executor based on their data locality. Then the executor registers themselves with the driver, providing the driver with a complete overview of active executors. So we can say that once these resources are allocated, this task scheduler deploys the tasks to the backend, which is nothing but to the worker nodes, and the driver establishes the connection with the worker nodes through the backend service, which is called deploy scheduler. So during this task execution, the driver monitors all the active executors and schedules the future tasks based on the data placement and execution process. Then the worker nodes execute the assigned tasks and sends the result back to the driver, and the output is tracked by a dedicated by this dedicated output tracker. So in summary, we can say that if we look at this, we will look at the role of this driver node. It communicates with the cluster manager to coordinate the resources. Then it negotiates with the cluster manager to allocate these resources, which is nothing but CPU and memory for the executors. Then it converts the Spark operations into DAG computations for the optimized execution. It also distributes the tasks to the executors on the worker nodes. And lastly, this monitors the task progresses, and it also gathers the updates directly from the executors. So this cohesive functionality ensures that this driver node will have the smooth operation of the Spark application within this distributed cluster environment. Now let's have a look at worker node architecture in detail. So the worker node is where executors reside, and it also performs the tasks which are assigned by the driver. So executors are launched at the start of this Spark application in coordination with the cluster manager, and then the driver dynamically manages these executors by launching and removing them as required. So the worker node contain multiple processes capable of running in parallel to execute these tasks scheduled by the driver. So these processes are nothing but the executors. Now we will look at this architecture in detail. So first thing is like executor as a JVM process. Each worker node runs on one or more executors, and each executors have their separate JVM process. So within a worker node, multiple executors can exist, with each having one or multiple cores for their task execution. Then the next is memory management. Because this worker node architecture partitions the data that are stored in On-Heap within the JVM drive within this JVM, and each executor stores the data in partitions of this processing. So this is about the On-Heap memory. And if we talk about the Off-Heap memory, it is managed directly by the operating system, and is also available outside the JVM. So the Spark supports storing this data into both On-Heap and Off-Heap memory. So if we talk about the advantages of this Off-Heap memory, we can say that data stored in Off-Heap memory does not require any kind of serialization or deserialization during read or write operations, which improves the performance. So unlike On-Heap memory, Off-Heap storage avoids triggering the JVM's garbage collection process, which is nothing but GC process. And this GC process can introduce the latency when scanning the memory to remove the obsolete or unused data by making Off-Heap memory more efficient for the certain workloads. So if we'll see this memory structure of an executor, each executor has its own dedicated off-heap memory, and off-heap memory is shared across the executors on the same node by providing the common storage area. So in short, we can say that this architecture ensures that it has efficient task execution and memory utilization across the worker nodes by optimizing the resource usage for Spark application. Now we will see into this memory management concept, which is of two types. One is on-heap memory and the second one is off-heap memory. So firstly, we'll see on-heap memory concept. So basically, memory management is a critical factor in performance of Apache Spark, we can say, because today we will, because we can say that on-heap memory refers to the memory managed by JVM, which is nothing but Java Virtual Machine, and it is a default memory used by the Spark unless explicitly configured otherwise. So this memory is divided into two parts or two areas, which first is storage memory. So the storage memory is used for caching the data such as RDDs and broadcast variables. We will have a look at RDDs in the next part. So the next one is execution memory, and this is used for operations such as shuffles, aggregation, and the joins. So since it is managed by the JVM, this garbage collection plays a significant role. So when objects are no longer needed, JVM cleans these objects using garbage collection. However, this process can bring some bottleneck for the performance in large scale applications, especially when we are dealing with the massive data set. So we can say that one of the major challenge with the on-heap memory is the garbage collection. So garbage collection pauses the application to scan and remove the unused objects, which can cause potential delays, especially in the application processing large volumes of data. And additionally, when the memory is full, Spark may spill intermediate data to disk, leading to slower performance. So now next we'll see and talk about the off-heap memory. So off-heap memory is allocated directly from the operating system and it exists outside the JVM. So Spark uses this memory to bypass the JVM garbage collection and reduce the memory pressure. So this is especially useful for the workloads that processes the large scale of data. So if we talk about some characteristics of off-heap memory, the first one we can say is manual management. So off-heap memory is managed directly by the Spark rather than JVM. This means that Spark must handle the allocation and cleanup explicitly. Then the next one is serialization. So data stored in off-heap memory is serialized into compact binary format. So while this improves the efficiency, it can also introduce additional overhead for the serialization and deserialization. And the next one is garbage collection free. Since off-heap memory bypasses the JVM, it avoids the garbage collection completely, which makes it more stable for the large-scale workloads. So why to use off-heap memory? Then the first one we can say or talk about is reduced garbage collection pressure. So by bypassing this garbage collection, off-heap memory minimizes this delays which are caused by the memory management. Then the next one we can say is efficient for large data set because it improves the performance when processing the large volumes of data by avoiding memory spills and the JVM conditions. And the next one we can say that a predictable behavior. So since the off-heap memory is managed outside the JVM, it offers more predictable memory usage, especially in memory intensive workloads. So here is the quick comparison between these on-heap and off-heap memory, which is getting displayed on the screen. So we can say that on-heap memory is managed by JVM. On the other hand, off-heap is managed outside the JVM. Garbage collection on-heap memory is managed through the garbage collection for because which can become a bottleneck, and off-heap memory is not subject to garbage collection. In terms of memory access, on-heap is managed by JVM and can be slower because of the overhead of the GC, which we have discussed earlier. And off-heap memory, it allows direct memory access, which can be faster and more efficient for the large data set. And lastly, about the usage in Spark, on-heap memory management uses the storing of RDDs, broadcast variables, and shuffle operations for the usage. And on the other hand, off-heap memory is used for storing serialized data, certain kind of metadata, and the crucial for shuffle and sort operations. Now we will look at this garbage collection concept in detail. So GC in Apache Spark, it plays a crucial role in managing the memory within the GVM by ensuring the efficient memory allocation and cleaning up of unused objects. So we can say that Spark application generate large volume of temporary and long-lived unused objects due to the operations like maybe shuffles, join, caching, which makes this GC essential for avoiding the memory overflows. However, insufficient or inefficient GC, it can lead to the performance of bottlenecks such as maybe increased pauses or the slower execution. So in Spark memory model, JVF heap is divided into two parts, which is first one is execution memory, which is used for the tasks like shuffle and the aggregations, and then the next one is storage memory, which is used for caching the intermediate results. So the garbage collection process, it has two phases. The first one is minor GC, it is for short-lived objects in the young generation, and then the major GC, it is for the long-lived objects in the old generation. So frequent GC events, especially major GC, it can result in stop the world pauses affecting the application performance. So to mitigate these issues, Spark employs the optimizations like maybe tungsten execution engine, which reduces the object's creation by leveraging low-level memory management techniques. And it also supports off-heap memory for storing outside the JVM, then the avoiding GC overhead and maybe reducing the need of serialization and deserialization. So effective GC or garbage collection, it depends on careful tuning strategies. So using this optimized GC algorithms like maybe G1 GC or adjusting heap memory regions or enabling like off heap memory, it can significantly improve the performance. Additionally, we can say that practices like maybe cryo serialization or minimizing the object creation and efficient caching strategies, it can also reduce the GC pressure. So monitoring tools like Spark UI, it also can provide valuable insights into GC activity, we can say, by helping to identify the bottlenecks and fine tune the configuration. So in short, in summary, we can say that while GC is a necessary process in Spark memory management, understanding and optimizing its behavior is also critical for maintaining high application performance, particularly for maybe large scale data processing workloads by using these tuning strategies. Now the next we will have a look at a Spark application workflow. So the provided diagram, it represents a basic life cycle of any Spark application, and it also shows the step-by-step execution process from the application submission to the termination. So now we will see each one of these steps in detail. So the first one is application, where the lifecycle begins when the user submits any Spark application. So this application consists of code to perform transformation like map or the filter and the actions maybe like count, collect on the large data sets. So the next one is the driver program, where driver initiates the Spark session. So this we can say that the Spark session serves as an entry point for interacting with Spark by managing the application and coordinating with the cluster resources. Then afterwards, the user-defined transformation and actions are passed by the driver and are converted into DAG, which is nothing but directed acyclic graph, which is nothing but a logical representation of any execution workflow. So this DAX scheduler optimizes the logical plan and it divides it into the stages based on this data dependency and shuffle boundaries. Then the next one is the executors, where the executors are the processes which are responsible for running individual tasks on this worker node. So the driver communicates with the cluster manager. Maybe that cluster manager would be anything like Yarn, Kubernetes, standalone, or maybe Mesos to request these resources for launching the executors. So in these resources, the executors would can be CPU or the memory. Then the next one is the cluster manager, where it allocates the resources to the executors, where we can say that cluster manager identifies the available resources across the clusters and it allocates them to the executors. So these executors are launched on the worker nodes and driver is notified for their availability. Then the next one is like once executors are ready, the driver establishes the connection with the worker nodes and it assigns the tasks based on the data locality. So these tasks correspond to the data partitions and are executed by the executors in parallel. Then executors on the worker nodes processes the tasks which are assigned by the driver, where they like execute the computations like transformations and the actions on their respective data partitions. So the results are sent back to the driver once those tasks are completed. And then after aggregating these results from all the worker nodes, driver sends this final output to the user, and if specified, the results are returned to the external storage systems like maybe HDFS, S3 or any databases. And at the end, once all these tasks are completed, the output is delivered, Spark application gets terminated, and the resources allocated by the cluster managers are get released and the executors get shut down. So in short, in summary, we can say that this execution lifecycle basically illustrates the coordinated interaction between driver, cluster manager, and the worker nodes to execute the distributed tasks efficiently. So it emphasizes Spark ability to process large scale data in fault tolerance, maybe parallelized and the optimized manner. So I think that's it for now. In conclusion, we can say that today we have learned that Apache Spark application exemplifies the efficiency combining with the distributed computing data, then the memory optimization and fault tolerance. So by understanding its components, memory management, and the workflow, we can effectively utilize this Spark for the big data analytics. So in the next lecture, we will try to learn more about the Apache API's, Spark API history, then the Spark ecosystem, then what are these RDD operations which we talked about like transformation and action workflows. Then we'll try to look at what is exactly lazy evaluation is, then the fault tolerance with the lineage, then what is DAG exactly, and what are the transformation types, which are nothing but narrow and wide transformation. So if you have liked my video, please like this video and subscribe to my channel for more such tutorials. Thank you, and till then keep crunching this data.